All right, so get ready because today we are diving deep into the world of solar cycles. You know, those fascinating patterns and cycles that the sun goes through. And we've got a fantastic excerpt from Wikipedia about it. It's like having a roadmap to the sun's wildest behavior. But before we get ahead of ourselves, can you give us a quick rundown on what a solar cycle actually is? I mean, is it as straightforward as the sun setting and rising each day?
That's a great question. And while the daily rising and setting of the sun are definitely important to us here on Earth, a solar cycle is a whole other phenomena. Think of it more like a cosmic heartbeat. The sun goes through phases of high and low activity, and these phases last roughly 11 years each.
Okay, so a cosmic heartbeat. I like that. But what are some of the things that signal the start of one of these high energy phases? Like, what should we be on the lookout for?
Well, one of the most obvious signs is sunspots. Those darker, cooler areas you sometimes see on the sun's surface. They might look small from Earth, but some can actually get bigger than our entire planet. And the thing about sunspots is, more sunspots equal more solar activity, more energy, more flares, the works.
More excitement, you say. That makes it sound like the sun throws solar flares, like confetti at a cosmic party or something. But on a more serious note, how did we even figure out this whole solar cycle business in the first place? Did some astronomer just accidentally leave their telescope pointed at the sun for a few decades?
Not quite that simple, but long-term observation definitely played a role. Back in the 1700s, a Danish astronomer by the name of Christian Horbaugh, he started to think there might be a pattern to these sunspots. But it wasn't until the 1840s that another astronomer, Samuel Heinrich Schwab, confirmed it. And he did that by meticulously observing the sun for over 17 years.
Wow, talk about dedication. Staring at the sun for 17 years straight to unravel its secrets, that's commitment. But you know what I find really interesting? There was actually a time when the sun went through this super quiet phase, hardly any sunspots at all. They call it the Maunder Minimum. And it lasted from 1645 to 1715. Can you imagine? No sunspot selfies for almost a century.
It really makes you wonder what other secrets those sunspot patterns hold. Speaking of patterns, there's this really fascinating visual representation of sunspot activity that scientists use. It's called the butterfly diagram.
Okay, a butterfly diagram. That sounds intriguing. But before we dive into that, can you give me the quick explanation? What are we talking about here?
So picture this. As a solar cycle progresses, sunspots start appearing closer and closer to the sun's equator, almost like they're following some kind of invisible magnetic pathway.
Yeah.
And when you plot this movement over time, the pattern that emerges looks remarkably like a butterfly.
So the sunspots migrate towards the equator during the cycle, creating this butterfly shape. It's like the sun has its own internal GPS and choreographer for these things.
That is incredible. And you said earlier that these sunspots aren't just random occurrences, right? They're actually signs of something much bigger happening beneath the sun's surface.
Exactly. Sunspots are like little windows into the intense magnetic activity that's constantly churning away within the sun.
Intense magnetic activity, huh?
Okay.
Okay, now we're talking. So it's not just the sunspots themselves, but what they represent. It's like this invisible force is shaping the sun's behavior. Kind of reminds me of those iron filings you sprinkle around a magnet in science class to see its magnetic field lines.
That's a great analogy. And just like those iron filings react to the magnet, our planet and everything around us are constantly being affected by the sun's magnetic field and all its fluctuations.
Whoa, so we're talking about like a solar influence that goes way beyond just, giving us a tan.
Yeah.
I'm suddenly feeling very connected to the sun right now. You definitely should. And this is where things get even more interesting. Remember those bursts of energy we mentioned earlier? Solar flares and coronal mass ejections. They're basically the sun flexing its magnetic muscles, sending out massive amounts of energy and particles out into space.
Okay, those were the ones that weren't about fashion choices, right? I'm ready to hear more about these blasts of energy.
Imagine this. 1 billion tons of solar material blasted into space at 1 million miles an hour. That's a coronal mass ejection, or CME. And they often happen alongside solar flares, which are these sudden, very localized explosions of energy on the sun's surface.
Okay, now that sounds like something straight out of a sci-fi movie. So what happens when these solar projectiles, let's call them, actually reach Earth? Do we need to, invest in some kind of planetary force field?
Fortunately, no. Earth has its own natural shield, its magnetic field, and that deflects most of those energetic particles. But that doesn't mean that we're totally off the hook.
There's always a catch, right? So what kind of effects are we talking about here? What happens when the sun burps and those burps reach us?
Well, think about it. We rely so much on technology now, and a lot of that technology is really sensitive to these electromagnetic disturbances. Solar storms, as these events are called. They can interfere with satellites, disrupt radio communications, even cause power grid issues in extreme cases.
Okay. Yeah, that's not ideal. So next time my internet's acting up, I can just blame it on the sun, right?
Well, not necessarily,
Hmm.
but increased solar activity can definitely play a role in those kinds of technological disruptions. It's a good reminder that even though it's millions of miles away, we're very much connected to the sun.
You got that right. And speaking of which, you mentioned earlier that these cycles aren't all created equal. Some are more intense than others, right?
Exactly. There's something called the Waldmeier effect. It basically says that the solar cycles with the biggest, most intense peaks, they tend to ramp up faster than those with weaker peaks. Think of it like a pot of water on the stove. A higher flame gets it boiling faster.
Okay, that makes sense. So a shorter ramp-up time to a bigger pick sounds like we might want to buckle up during those cycles. And then there's that whole thing about odd-numbered cycles being more intense. What's up with that?
That's the Nevi-Chevol rule. And it suggests that when we look at pairs of these solar cycles, the total number of sunspots tends to be higher in the odd-numbered cycle compared to the even-numbered one right before it
I
due.
got the sun. The sun has a preference for odd numbers when it comes to drama. I like it. But things are about to get even more interesting, right? Our Wikipedia source mentions something called the Gleissberg cycle, and this one spans over several solar cycles. Talk about long-range forecasting.
Now, the Gleissberg cycle is where things get really interesting. It suggests that the intensity of these cycles, it's not uniform over very long periods. Instead, it proposes this cycle of about 70 to 100 years, which includes something like 7 or 8 regular solar cycles. And during that time, the peaks of those 11-year cycles, they themselves fluctuate in amplitude.
Okay, so it's like we have a solar cycle of solar cycles. We're going meta with this. So it's not just the regular rise and fall of sunspots. We've got this whole other pattern of stronger and weaker cycles playing out over generations. It's like the sun has its own internal saga going on.
Exactly. And what's amazing is that scientists have found evidence of these long-term fluctuations by looking at things like tree rings and ice cores. These natural archives can actually give us clues about past solar behavior, going back thousands of years. It's like they're cosmic time capsules, preserving the sun's history.
Wait, so we're talking about like looking for solar fingerprints in the growth patterns of trees and the composition of ancient ice. That's some serious detective work. It's amazing that we can look back in time like that.
Hmm.
It really makes you wonder what those trees and ice sheets could tell us about how the sun has affected Earth's climate. I mean, we talked about how solar storms can mess with our technology, but could a really strong solar cycle actually change the entire planet's temperature?
That's a great question. And it's one that scientists are still trying to figure out. There's some evidence that periods of really low solar activity, like that Maunder Minimum we discussed earlier, might be linked to slightly cooler temperatures here on Earth. So if we're potentially heading into a period of unusually high activity, it really makes you wonder what that could mean for our climate models. It's a complex puzzle for sure.
It's pretty amazing when you think about it. This giant ball of plasma, millions of miles away, could have such a big impact on our planet. It really shows how much we still have to learn.
It definitely does. And every new thing we learn about solar cycles seems to bring up even more questions. That's part of what makes this field so fascinating. For instance, we've uncovered all these incredible patterns in solar activity. But the big question is, can we actually predict them accurately? And what happens if we get it wrong?
That's a little unnerving when you put it like that. Imagine if we could predict a major solar storm in advance, though. With enough time to prepare our power grids and satellites, we could potentially avoid blackouts, communication breakdowns, all kinds of headaches.
Exactly. Being able to accurately predict solar cycles is essential, not just for our technology here on Earth, but also for things like space travel. Can you imagine sending astronauts on a mission to Mars during a period of intense solar activity? Talk about risky.
Yeah, no kidding. So are there any like early warning signs we can look out for? When it comes to solar storms, I mean, what are scientists keeping an eye on?
One of the biggest indicators is when we see these large groups of sunspots, ones with really complex magnetic fields. Those are often the areas where solar flares and CMEs originate. Scientists use these incredibly powerful telescopes and imaging techniques to monitor those regions really closely, looking for any hint that an eruption might be imminent.
So it's kind of like we're constantly keeping an eye on the sun, making sure it doesn't throw a cosmic tantrum and cause too much trouble. Well, that was fascinating. A crash course in the sun's sometimes unpredictable and always fascinating behavior. From those migrating sunspots to those powerful solar flares that can mess with our technology, the sun is definitely a force to be reckoned with.
And we can't forget about those long-term cycles, like the Gleissberg cycle. They remind us that the sun has its own rhythm, its own story, a story that's been unfolding for billions of years and continues to shape our planet in ways we're still just beginning to understand.
It really puts things into perspective, doesn't it? We're here living next to this star with its own epic ancient history. A history written in sunspots, solar flares, and those subtle clues we can find in things like tree rings and ice cores. And as we've learned today, that story is far from over. Thanks for joining us on this deep dive into the heart of the solar system. We'll catch you next time when we explore, well, who knows what other mysteries await.